Good evening, everyone.
Good evening.
We're starting a new chapter. Actually, there's 2 chapters to go. There's 13, this one. And then we've got a little bit of 14. The thing about chapter 14 is it's an overlap with Calc 4. Right, so once you've done the beginning of chapter 14, when you do, at least if you get me, when I do it, when you get Calc 4, I start off at the beginning of chapter 4, so a little overlap there. So this is our major one that's all in Calc 3, and we are going to look at functions called vector functions. They also have another name which I prefer actually, and they're called space curves as well. So a little definition and a really bad drawing picture. A vector function, also called a space curve, typically they're written using vector notation. So in a textbook, this would be a bold RT. So it is a vector, mostly 3-dimensional, certainly multi-dimensional, more than one. And so a vector function R of t, also called a space curve, is a multi-dimensional function in terms of a single variable t. So here is a random example of a space curve. R of t is t cubed, that's the x component, sine t is the y component, and e to the t cosine t. Now this is a vector, and it's actually a position vector, which is a very special kind of vector, because essentially a position vector is like coordinates. It tells you the vector from 0 to that point. Well, if you go t cubed in the x, sine t in the y, and e to the t cosine t in z, would you agree it's just your x, y, z coordinate, right? So from the origin to that point. So there's it is a vector, but you can also think of it as it tells you the coordinates of a point in any given value of t. Most of the ones you're going to deal with are 3D, occasional 2Ds pop in. You could theoretically do 4D. So I want you to imagine that's our XY plane. This is your space curve. This is your vector function. It has an orientation. The orientation just means how does it travel along the curve? Because there are 2 orientations. There's the one that you can see here, but can you also be going down the curve that way? Space curves are very good for modeling objects in 3D space, spaceships, asteroids, satellites, you name it. It moves in 3D space. You could probably generate space curve for it, right? A vector function. So far, so good. That's what it looks like. So can you imagine at t equals 0? Let's pretend this. T equals 0. Its location is here. Then at t equals 1, its location is there. That's how you decide orientation. Just find out where it is at, say, t0 and t1. And if it's there at t0 and there at t1, well, you kind of know what it's going to do for the rest of its life. Are we cool? Right. Now, we've got a lot of things in this one section because it's kind of an intro. In fact, I've just done the intro. So next thing we're going to look at is what's the domain of a vector function? What is its domain? Right. Way back in 141 was probably the first time you came across this idea of a domain of a function. In 141, wouldn't the domain be the usable values of x, right? For what values of x can you plug into the function and actually get a number as your answer, right? Well, when you talk about the domain of a vector function, it's really just the same idea. It's the usable values of t, right? So for what values of t does this exist, right? Can I actually plug numbers in? Now, it has to be a value of t that works for all 3. It's no good that I can plug in a number and it works for this guy and it works for this guy, but this doesn't, right? That wouldn't be included in the domain, right? It has to work for all 3. So the way that you calculate the domain is you take the x component, that's what this guy's called. You take the y component, that's what this guy's called, and you take the z component, and you find out what the domain is of each of these in terms of t. So I'm going to just pick one at random. 2 to the power of t. Would you agree you can use any value of t you like and this will exist, right? It will be a number. So in this case, the domain is everything. And the easiest way to do everything using interval notation would be that. So far, so good. Now, there are, and some of these are a bit rusty for you, but there are domains for these two functions, but we have to kind of know what's going on. If you do a log of t, right, just the natural log of t, it looks like that, and it crosses at 1. And as long as you keep away from 0, that would be the domain of log t. But I have the log of t plus 4. Now you could probably plug that into Desmos or something similar and see what it is. I just want to do it this way. Do you move this shape left or right by 4? Because that's the guy that's really important. So it says t plus 4. Do we move it left 4 or do you move it right 4?
Left.
Left. It's counterintuitive, doesn't it? Sound like adding should move right, but it's not. You move it left 4. So I am going to take as many pieces of this shape and imagine them being shifted to the left. The first thing I'm going to do is, do you know the y-axis is like a vertical asymptote? I'm going to move that to the left and it ends up being here. Make sense? Now, the only important number apart from the shape, which is important, is that number. And if I move that guy, he gets to there. So if I was wanting to do a very rough sketch, would you be comfortable that that's roughly what the natural log of t plus 4 looks like? Great. Now, when I see the red picture and I want to talk about its domain, and I guess I should call that t, really, right? If I want to talk about its domain, would you agree as long as t is bigger than -4, you're good? Right, now bigger than -4 means that guy. So the domain of this fella is anything that's greater than -4. Right, we get a guy in the middle now. It's a rational function. Now, when you're thinking about what makes this guy, you know, what values of t will this work for? The key is this guy here. So I'm only going to focus on what values of t I can use in that function. Now, if it's a square root, doesn't that mean that the guy inside has to be greater than 0? Now, normally you would say greater than or equal to 0, but since this is a fraction and this guy's on the bottom, I don't want it to equal to 0 because that will cause its own trouble. Now, if you put this guy and you do a very quick sketch of him, can you trust me? That's what he looks like. Okay. And it's greater than 0 from here to here. So the domain is numbers from -5 to +5. So over here, we've got -5 to +5. So after a fair amount of work, we got the domain of this guy, the domain of the y component, and the domain of the z component. And now we have to merge them together and figure out what is the values of t that will work for each of them. Well, that one's easy, right? Anybody will work, so I'm not worried about that one. I'm really more interested in how these two things overlap. So this says it has to be -4 or bigger. And this says it has to be between -5 and 5. If you merge these two together, so both things are true. Anybody want to tell me a start number? Because it is a number. What goes here?
-3 to 5.
Say again?
3.
It sounds like you're saying 3.
-3, sorry.
I can't see a 3. Why would you choose that?
I don't want to overlap it with the natural log of 4. Oh, wait.
Oh, but you can go as close as you like and not overlap.
Oh, I see.
So you right. So how about -4? As long as you don't use it, you're okay. So where would you finish? I think you said 5, didn't you?
I did, yes.
And that's a good answer. Are you comfortable then that the values of t that work in all 3, right? So it'll work for this one, and this one. You can only pick numbers in a very narrow band, right? From -4 to 5. You can't even use the ends, right? You can have -4 or 5. And that is the domain of a function. Or at least that's how you calculate the domain of a function. Are we good with that one? Right. There's only 2 of those questions, and I've basically done question 1. So, or at least a version of it. So let's move on to the second topic. Oh, I'm too quick. Was there anything in this process that wasn't clear that you might want me to elaborate on? Are you comfortable at how we found this domain, how we found this domain, and how we found this domain, and then how we kind of matched them together? Let me show you, because not everyone sees numbers. Imagine this number line are the values of t that you can use. Right, this one here says use everybody. So it would be this red line, right? This guy says, nope, you can't use everybody. You have to start at -5, put a 0 in the middle, right? And you have to finish at 5. So that means it has to be those kind of numbers. Now, if you put those 2 restrictions together, isn't the green line the only one that works? Now, if you superimpose upon that, this fella, -4 to infinity, I'm not got really any more color, so I guess it's red again. From -4 to infinity would be that guy. Now, you want all of them to work. Don't you have to start there and finish here? And that's the domain that I came up with. Does that help you to visualize it a little bit better? Right? Sometimes pictures are easier than words. Okay. Move on then. The next thing we're going to look at is how to find the limit. So what's that in my list? Number 3. How to find the limit of a vector function. So this, I think, would come under Calc 1. So let's show you what that guy looks like. Let's do a version of equation 3. And so we're being asked to find the limit as t tends to 0 of e to the -4t, t squared over sine squared t, and the tangent of 5t. Right, so we want, I'd actually put those brackets in, but whatever. WebAssign decide that curves work as well. So there's my space curve. You see it? It's got 3 pieces. And I want to find out what's the limit of this expression, this space curve, as t goes to 0. There are 3 major techniques that you've used when you did limits in Calc 1. One of them is essentially brute force. You just plug the number in, and if you get an answer, you're good, right? The second one is L'Hopital, right? Right, differentiate Totenbaum. And the third one, hopefully you won't need to do it, but it's called the conjugate method. Now, if you want to find the limit of this, what you do instead is you just find the limits of each piece separately, and then you get your answer. So here's the three pieces, right? The X, the Y, and the Z component. I'm going to do this one because it's easiest. Brute force says it's the tangent of 0, which is 0. That was easy, right? And I'm going to do this one. Is it not 4 times 0 is 0, and that's 1. Any suggestions about how to take care of this horrible guy?
L'Hopital.
You could do L'Hopital. Yeah. Now, if I did L'Hopital, can you trust me this is as ugly as heck, but eventually you get an answer? And can you just trust me the answer's 2? And you have to do it twice in a row. But can you trust me? I don't want to do it. It takes me about 10 minutes, but it does work. So this means that the limit of this expression is simply just 1, 2, and 0. So as long as you can remember your techniques from Calc 1, you should be able to find the limits of each expression separately. So that's the limit as t tends to 0. The other one, number 4, is doing the limit as t tends to infinity. And it's going to be that guy, this guy, and finally, this guy. There's a minus in there, so it's 5 take away that. But we can still do the same strategies. You take each one of these in turn, and you can do a brute force on it, or you can do a L'Hopital on it. There aren't any square roots, so we don't need to worry about that method. So here goes the first one. Give me a method to do. I just thought you a new one you could probably do with this, but give me the method for this.
T squared.
You get broke off, Lewis? What did you say?
Divide by t squared.
Oh yeah, that's the extra one I was thinking about. You could do L'Hopital, it works too. But if you do it this way, you get that fella, and you get that fella. And then if you make t infinite, you get 0 plus 1, 0 minus 1. So the answer is -1. This one causes problems because people forget that the inverse tan of infinity is actually a number. So I'm brute force on this. What is the angle whose tangent is infinity? That's what inverse tan is.
That it's the pi over 2, right?
Yeah. So in this case, that's the answer. And for the last piece of the puzzle, we are going to be looking at this guy. How are you going to do it?
Can
You
you
can do
take
the L'Hopital, right?
Certainly you could do L'Hopital because you can kind of do L'Hopital for any fraction. But sometimes just because you can doesn't mean you should.
What
about brute force?
Let's do a brute force. 5 take away e to the power of negative infinity all over infinity. I know it's a weird calculation, and very often if you try brute force, you get a calculation that's impossible to do. You ain't not infinity over infinity, right? If you see an infinity over infinity, it's called an indeterminate form, in which case you should do L'Hopital. But this one, I don't think I need to do that. E to the negative infinity is 1 over e to the infinity. What does 1 over e to the infinity get you as a number? And it is a number.
is 0.
So what you're going to get is 5 over infinity. And what does 5 over infinity get you? Because it's a number.
It is the same as the previous one, which is 1. Oh, sorry, 0.
Same as the previous answer, it's a 0. So the limit of this expression was -1, 5/2 pi, and 0. Are we good? So if you want to find the limit of space curve, you basically have to find 3 separate limits. If you want to find the domain of a space curve, don't you have to find 3 separate domains and then kind of combine them into a single interval of t? Anything about that you want me to talk about, or are we good?
So is that finding the domain of
Yeah,
the?
This,
space
you know,
curve?
this is finding the limits.
All right.
Right, we're finding, in this case, the limit is t tends to infinity, and in this case, the limit is t tends to 0. But the methods are very similar in many contexts, right? You can brute force and L'Hopital, right? Could have done that. I could have done this, by the way, as L'Hopital, and it would have worked. I think you should be careful about doing this guy with L'Hopital, but I think it would have actually worked. You'd have to check it, but I think you'd get 0, in which case it did work. Are we good?
I have
Yes.
a comment to make.
Go for it.
My internet's going really wonky, so I might be cutting out in and out.
Okay, Jeremy, since I know you're honest and I know you're here because I'm talking to you, you might want to put your name down just in case it
All right.
really keels over and dies.
Thank you.
Okay, so chalk it off our list. Not many examples of them, but we've done domain and we've done limits. Now there are a big chunk of questions all about sketches, and then a little one about when does a space curve intersect a 3D surface. The next chunk of questions all involve us using some software. So if you give me a few seconds, I will show you. I want that one to go away. How do you make things go away in this thing? Just hit X. No. There we go. Okay. I had to make one of my earlier ones disappear because I don't want you to see it until it's time. So I'm using GeoBra, and we're going to do it to do space curves. So let's suppose I wanted to do a space curve. You do a little curve bracket, and let's suppose it was t squared plus 1, comma, the sine of t, put in a little bracket because it needed it, followed by 2t take away 1. Now, that's, may have to open this up a little bit because there is some stuff hidden behind it. There we go. You see that this is their standard t value. Do you see how they put t equals -10 to 10? If you only want to do positive values, you could change this guy and just do 0 to 10. Hopefully it'll change it over. Okay, if it should change it over, there we go. Now, it's not the most interesting space curve in the world. You see it's just basically like a bit of wire. Now, if I wanted to know its orientation, in other words, does it start off here and curve upwards? So is it like the trajectory of a rocket leaving, the surface of the Earth? Or do I want to do this one coming down, which might be the path of an asteroid smashing into us? Right? So how would I decide, is it going up or coming down? Right? Well, you just figure out where it would be at t equals 0. So if I plug t equals 0 in here, it would be at position 1, 0, -1, which is essentially there. And I bet you if I did, well, I don't actually need another one. Would you agree the rest of it has to be going this way? But if I calculated one, t equals 0 would be, there we go, would be there. And then 1, and then 2, then 3, then 4, then 5. Do you see the orientation? It's really cool at generating essentially curves in 3D space, isn't it? The way they write them. So let me show you a very common one. I'll just hide that one. It saves me having to rub it out. And this time I'm going to put in 2 sine t, comma, 2 cosine t, comma, t. And I'm going to expand this a little bit. I'm going to make it, I don't know if that's too many, but I'll find out. I'm going to make it go 0 to 20 pi. Oh, well, you can't see the rest, but if I orientate it, do you see that's a circle if you were flying above it? But it's really like a corkscrew, isn't it? You see it? Orientated. Now, if I wanted to see more of it, because the y-axis only goes up to 6, I could go over here. I believe it's, is it in this one you do it this way? Oh, there we are, settings. And I could do the Z values, and I'll make them -4, and I'll make this guy a lot bigger than 6. Let's say 40. And when I come out of that, I want to see, oh, good. There, can you see my helix? Because that's what we call these. I mean, is that not cool? If I wanted to model the spring in a truck, wouldn't it be pretty easy to do it as a helix? Now, if I'm putting you in the spot and I don't know what the answer to this question is going to be, but you've got a 3D printer. When you do a 3D printer, you put in the equation of things, don't you?
If you want to go like old school and do the G code manually, you would have to do. What you would do is you do the model, and then the model you would put in the equations and stuff to get the dimensions you wanted, and then the G code would be generated for the printer.
So when you put in the model, if I wanted you, not that I want you to, but if you wanted to make a spring, could you use the space curve information, or would you have to code it in a different way?
I could use that information when I told the program how I wanted the spring to look.
Right. Because this is essentially is an infinite thin piece of wire, right? So you'd have to build thickness to it. So does that look like something you might play about with if you were interested in doing it? It'd be a very expensive slinky. Now, this particular helix is orientated on the z-axis, right? That just means the vertical one. Of course, if you change the location of this guy, the third one, which is T, if I rub this guy, well, actually, let's just keep that one and cheat. Let's just copy this curve. Hopefully, it'll let me copy it. And just change the T and put it in the middle. Oh, we can't see the orientation because of my restrictions on the X and Y axis. So I'm going to do this guy to -6. And that might help a little bit. Okay. If I orientate this, can you see the other one now? If I orientate it in a different orientation and make this one hide, you see it? Wherever you put the T, this particular one is actually traveling along the y-axis, but it's not got an awful lot of room because I didn't move the windows. And if I do this, there, can you see it a lot better now? And if I do it side on, I'm not sure you can actually see it side on. There, you see it now? So you've got a whole load of questions, and basically they all fall into the category of here is a space curve. Here are 4 pictures. Which one am I? That kind of question. So you would go here, put it in, play about with the window so you've got it in, you know, a size that you can see it, and then pick the picture that looks closest to it. So I'm trying to think if it's this one. It is this one, right? So let me make sure that you can see what I'm saying. Right. Here is our question. Now, do you see that's a 2D one? You know, you can do 2D ones, just have 2. Let's skip to the 3D ones because they're more interesting. There's some more 2Ds. That's another 2D. Where's the 3D ones? Oh, there's a 3D one. And it's either that guy. Was that it? Just 2? Oh, okay. That's pretty boring, actually. Yeah, mine isn't updating well, but isn't that just another way of telling you X, Y, and Z? And so if you plug that in as bracket T, comma, this fraction, comma, T squared, you would get a space curve. And it would, if this darn thing would work, you'd see a spiral or whatever it is and you'd pick it. I'm not sure if this is a function of Zoom not reading this page well, but can you trust me? There are pictures here that you could look at, and one of them would be the guy you want. Oh, see, there's one, just to be awkward. Some of them work. These ones are not as good as that, but you know, if you touch on them, you can actually orientate them. So it's a little bit of movement, not the best, but they're different unusual helixes. Okay, can I just say you're going to have a lot of fun playing about with GeoBra and looking at pictures and picking the right one. Now, I think since there's probably only 4 pictures to pick, you're probably going to get them all right eventually because you get 5 guesses. So you're probably going to get them all right. So the last thing I want to, you know, talk about, and then we're moving on to our next section. So this is quite a short section, is when does a space curve, that's this guy here, intersect with a 3D surface? So imagine this is a version of question 12, so you only get like one shot at it. Here is my space curve, kind of written in its traditional way. So there isn't anything in the middle. Okay. And we're being asked to find out where this space curve intersects with that guy. Now, if you put that into GeoBra and actually look at it, which is something I'm going to do in a few moments, I think, after we've solved it algebraically. This is roughly what that guy looks like. You know, it looks like a cup or an acorn. Can you imagine a cup going upwards like this? Right, that's what that looks like. And here is a space curve that's going to come in, and I'm making no attempt to do this accurate. It's going to come in and intersect it, travel through the inside, and then make a hole on its way out. Right, it's probably got a curve to it, right? So our job is to find the 2 places where it works. And I know there's 2 places because the question gives me space for 2 answers. So here's your puzzle. How do you find out where that surface and that curve intersect each other in 3D?
Can you repeat the question?
Yes. How do I find the coordinates of where this space curve intersects this surface? Any suggestions algebraically how I could do that?
Oh, okay.
Somebody start?
I was thinking about how we were doing the homework the other day, where you set all that equal to its X, Y, and Z values, since you already have them in the equation.
Yep, that's how you do it. So X, Y, Z. So Z is 3t take away t squared. X is t, so x squared is t squared, and y is 0. So you got that. If I add a t squared to both sides, I guess I get that. If I then subtract 3t from both sides, I get that. Probably made that harder than it is. Pull out a common factor, then there are going to be two answers. One is when t equals 0, and the other is going to be when t equals 3/2. So far, so good. Right, I need to turn these into coordinates. And one goes in the first box, and that's the one that uses, they call it the smaller t. So I'm assuming that means t equals 0. And then the other one is that guy. So how do I now find what the coordinates are? I found the t values where the curve meets the surface, but how do I get that information and convert it into coordinates of where these things are?
You plug it back to the original function that you just made, right?
Yeah, so t is 0, gets me 0, that's still 0, and that's 0. Question? When are they closing? Can you, you can't do that, can we? Okay. I apologize, everyone. I have a kind of, it's not a serious, but I have a kind of family emergency thing. So plug 3/2 in there, get it done. It was nice that we finished the first one. What I'm going to do to make up for the next section that we would have been starting today is that sometime tomorrow, no, it can't be tomorrow. Oh God, how am I going to catch up? Because we can't afford to lose time. Right, when we see you tomorrow, we're going to continue with what we would have been doing. And